Mr. Chairman, honorable guests, ladies and gentlemen, it's a very pleasure for me to be able to attend this meeting. Today, I'm going to talk about our paper, M2M, Learning to Enhance Low-Light Image from Model to Mobile FPGA. I'll introduce our work from research and motivation to conclusion. Let's kick off on research and motivation. In computer vision, low-light image enhancement plays a key role in displaying clarity and integrity visual information from poor visibility environments. With the development of convolutional neural networks, the effectiveness of low-light image enhancement techniques have been greatly advanced. However, the calculate-intensive and memory-intensive characteristics of convolutional neural networks make most of the work to be based on large indoor servers. This obviously does not meet the needs of security, latency, and stability. From the past to the foreseeable future, high-quality image acquisition is always an important computer vision task and serves as an bias for the following image detection, recognition, and understanding tasks. Meanwhile, many real-time industrial applications cannot meet the hardware requirements for these deep learning approaches. Therefore, hardware-based low-light image enhancement research is in great demand. This paper proposed a complete solution for low-light image enhancement from model to mobile FPGA. The proposed solution outlines a pseudo-symmetry condensation method to compress the low-light image enhancement model, and an accelerator to permit the processing ability of the system significantly. We implemented the whole system on a customized FPGA SoC platform, which has a low-cost chip, Zinc XC7Z035. In the software technologies of model quantity compression, some works have shown that the inference of CNN can be accelerated using approximate value computation. And operands of CNN can be reduced without seriously affecting the inference performance. The throughput rate and energy efficiency of the computation are improved by a minimum number of weights precision to reduce the total amount of bandwidth required to relieve the bandwidth pressure. In addition, there are accelerations designed by buffer management, bandwidth optimization, and other methods have been proposed. This hardware direction targets to accelerate the system computation by full utilization of resources on FPGA. With the proposal and development of general-purpose frameworks such as Caffe, TensorFlow, and PyTorch, existing deep learning-based low-light image enhancement tasks are mainly focused on large general-purpose chips, such as GPU. Early on-chip works mostly focused on handwriting digit recognition and image classification. Adapted to the memory storage on FPGA, these solutions are all true small models with 2 to 5 convolutional layers, which is much shallower than the networks in GPU-based methods. In recent years, LSTM-based speech recognition and YOLO-based object detection have been introduced on expensive FPGA. Obviously, higher accuracy and better visual perception obtained on FPGA for low-light image enhancement need more complex and deeper CNN. However, state-of-the-art on-chip low-light enhancement work is based on the AHE method. So, our work is a brand new attempt, implementing CNN-based low-light image enhancement on FPGA. And then, let me show you our method. Overall system framework design. The framework design mainly consists of off-chip memory, off-chip interconnect, on-chip buffer, on-chip interconnect, acceleration processing unit, and LEC processing unit. First, we store all the data to be processed in the off-chip memory DDR3. Due to on-chip resource and bandwidth constraints, the data is first cached in on-chip buffers before being provided to be communicated through the AXI bus and the acceleration. We design a double buffer for weights and feature maps data to cover the computation time and data transfer time. PE is the basic computation unit within the convolutional acceleration. The on-chip interconnect is dedicated to the data communication between PE and the on-chip buffer. Finally, we splice all the enhanced pixel data in the cache and return the output as the final image result. Quantization can reduce memory bandwidth and storage space, and deep learning models mainly record weights and biases for each layer. In the float-point 32 model, each weight value originally requires 32 bits storage space. But after quantization, only fewer bits are needed. This means the lower precision inference process will significantly reduce the memory access bandwidth requirement and improve the cache hit rate, especially for memory-bound element-wise operators such as batch normal, ReLU, element-wise sum, and so on. In short, quantization is the process of mapping values from one whose domain is usually continuous to another whose domain is usually containable and contains much less values. Finally, we control the overflow of data by fixed point. Acceleration processing unit architecture design. Our input and output data are stored in FM buffer, and the weights and biases are stored in weight buffer. The number of FIFO keys and registers are specially allocated based on resource usage and computational requirements. First, the load imbalance of the weights after quantization will reduce the hardware efficiency. Different factors will be consumed by multiple PEs, so the operations of all PEs must be synchronized. On entry to PE, we map a path length of data directly to the registers in one clock cycle, reducing the extremely time-consuming read operations. This will lead to critical clock disorder, and we stabilize the clock by skipping the compute and write operations in that cycle with a small amount of weight. In this design, we are free to exploit the parallelism of operations between processing units. The accelerator should be carefully designed for data index, and the data width of the external DDR3 memory interface and the data itself must be well aligned. Experiments. We follow the work of 0DCE for the network structure design and training. 7 symmetrically spliced convolutional layers were used to form the CNN, each layer containing 32 convolutional kernels of size 3 × 3 with a stride of 1, followed by a ReLU or TOM activation function. We implemented our system design on a Xilinx custom development board with a dual-core ARM Cortex-A9, a Zinc XC7Z035 FPGA, and 1 GB of DDR3 SDRAM storage. The on-chip resources are shown in the table below, which makes it a low-cost development board with few resources. For full reference image quality evaluation, we use the EVO 15 dataset for testing. PSNR and SSIM were used to quantitatively compare the performance against different methods. Figure below shows the percentage performance degradation of the different quantization schemes. The full precision performance without quantization is subjected to only a little machine degradation. Both 4-bit and 8-bit quantization schemes show significant degradation in quality evaluation results, and the 16-bit quantization schemes is the best. Quantization schemes restore the enhancement of low-light images as much as possible, while decreasing the computational and storage requirements, and the degradation of both evaluated results is kept within 10%. We give the visual comparison of typical low-light images under different quantization schemes in figure below. 3 different quantization schemes compared to ground truth and full precision results. It can be seen that due to the reduction of weight precision, the 4-bit quantization scheme almost loses the enhancement effect and cannot distinguish the details and colors. The 8-bit quantization scheme has little enhancement effect on the low-light images, and it is difficult to restore the details and colors. While the 16-bit quantization scheme reduces the computation and storage requirements, while maximizing the restoration of the low-light image enhancement effect, which is the best solution. We give a visual comparison of another state-of-the-art FPGA-based AHE methods with the results of our 16-bit quantization schemes in figure below. By implementing CNN-based methods, we achieved better effects in brightness, color reproduction, and realism. We give a visual comparison of other state-of-the-art GPU-based methods with the results of our 16-bit quantization schemes in figure below. We compared with EliteGAN, Kind, RetiNextNet, and ZeroDCE. Our FPGA-based result enhances the visual perception intuitively, strengthening the dark areas and preserving the original image colors without significant noise and chromatic aberration. In table below, we compared our approach on FPGA with other platforms. We chose the Titan GPU, an Intel i7 CPU, and Cortex-A9 ARM for comparison. Compared to ARM, we are 41 times faster and 99 times power efficient. Compared to the CPU, we are 38 times faster and 40 times power efficient. And compared to GPU, we are 1.2 times power efficient. Consequently, our approach is suitable for low-light image enhancement on mobile platforms. Here we make a conclusion. As the best of knowledge, in this paper we present the first method for deep learning-based low-light image enhancement on FPGA. We show that the enhancement on a low-cost FPGA chip is comparable to existing state-of-the-art works on GPU. We analyze the distribution of model weights and propose a solution to the difficulty of quantized compression of low-light image enhancement model weights. We propose an accelerator for CNN-based low-light image enhancement, which eases the on-chip conflicts between limited computation power and increased cost. Thanks a lot for listening. If you have any questions or thoughts, please do not hesitate to let me know. Thank you.